Hi, I'm David Booth. Today's webinar by Harold Solbrig continues our series of webinars about the Yosemite Project. The Yosemite Project is a collaborative effort whose mission is to achieve semantic interoperability of all structured healthcare information. It articulates a roadmap for achieving interoperability based on RDF as a universal information representation. In today's webinar, Harold Solbrig will discuss work that he's done at Mayo Clinic to combine use of FHIR RDF with other ontologies in a reasoner to identify patients with certain diagnoses, such as cancer. The effort to create a standard RDF representation of FHIR falls into the Standardize the Standards theme of the Yosemite Project. Harold Solbrig's work at Mayo Clinic helps demonstrate what can be achieved through the use of RDF as a universal information representation for healthcare data. Harold has been involved in medical computing since the early 1970s. Over the past 2 decades, his emphasis has been on the role of formal semantics in data interoperability, and he joined Mayo Clinic in 1999. Welcome, Harold.
Thanks, David. Okay, today what we're going to do is talk a little bit about RDF and FHIR, kind of an exciting new development. The fact that you can get FHIR information in the RDF format, and then touch on one of the many possibilities, which is now that we have it in RDF, how we can use a DL reasoner to start to classify and categorize information that comes through FHIR. And then finally talk about where we are, where we're going, what we've found out, etc. FHIR, I'm hoping most people on the call are familiar with this. The jump-off point is right there. It's been in operation for, I believe, 4 years now, and is rapidly becoming the de facto mechanism for exchanging clinical data. This is the home page of the FHIR resource. In fact, I just realized I need to cut this slide down a little. There we go, good. And I've got a circle down at the bottom there where I'm going to jump into the diagnostics area of FHIR. This is a sample FHIR resource definition. If you click through that previous link and scroll down, what you've got here is it's a structured definition of a FHIR diagnostic report. It's a model of the various things that can be shown. This is the FHIR model. They actually use their own modeling paradigm, meta model called structure definition of a FHIR resource definition. Now they have a specification that says how an instance of a FHIR resource definition is rendered in XML. So I've picked a particular example of this is a diagnostic report, a brain CT scan, and called out 3 fields that we're going to keep focusing on again and again in the rest of this talk. The first one is the status of the report itself. So in XML, you can see status value equals final. The subject of the report, the fact that it's a reference to a patient with a descriptive identifier of F201 and the name of Raul. These are just samples that are on the FHIR site. And a coded diagnosis, a diagnosis where they've said we found a large tuber of the sphenoid in clevus, and the coding is a malignant tumor of the craniopharyngeal duct. This is what it looks like in JSON. Again, this is a FHIR specification. It says when you render it in JSON, you will do exactly these things. So you can, looking at this model, you know exactly what you're going to get out of JSON. Showing again the 3 links. You'll notice below, let's see on the previous slide, you can get, for this model, you can get a combination of XML and schematron that defines what the XML looks like. When it comes to JSON, there's a link for JSON schema, but that hasn't been completed. There's been discussion about having a JSON schema model, but there it is. Okay, as of version 3, you can also get, there's a specification that says what an instance looks like in RDF. This is exactly the same record, and this is the RDF rendering. We have the status, the subject, and the coded diagnosis. Now there's a couple of extra things that show up there that I'm going to talk about in a minute. Just as an aside, you can also get the definition for what the RDF looks like in the shape expressions language. The link is down below. On all of these slides, I've got the URLs that if you dereference will take you directly to the resources. Before we proceed, I'm assuming that everybody here knows about RDF. I'm not sure whether everybody knows about the turtle syntax, so I just wanted to take a quick side trip. Turtle allows you to define prefixes so that instead of the full URL, HTTP, HL7.org, FHIR, you can just use FHIR : and that's the equivalent of a full URL, such as what's shown in the subject. If you encountered the letter A, it's just a shorthand for RDF type, convenient to help with semantics. Semicolons say that we're going to have another predicate object following the subject. So the subject is this diagnostic report F201. We say it's a type diagnostic report, and then F201 has node role tree root, F201 has resource ID, etc. The open and closed brackets represent blank nodes. They hide much of the evils of blank nodes, but realize that this says it's a real resource ID of a blank node, the blank node of which has a predicate of FHIR value and an object of F201. And you'll find commas separating things as well, and that's the case where you've got subject, predicate, object, and then another object with the same predicate. So in this case, it's a coding, and it's got two instances. Both are blank nodes. The first coding is this instance, and the second coding is this instance. A quick touch on, I put maturity in quotes for the syntax maturity. The RDF rendering is fairly recent in FHIR compared to the XML and JSON. So it's at what they call a maturity level 2. We've got some tests and some semi-realistic data, and we're looking to continue to use it, to continue to test it, and get it in a formal specification, etc. As of these slides, I don't believe there's anything in FHIR that is normative. The highest maturity level for anything you'll find is maturity level 5. Okay, the FHIR RDF rendering, one of the requirements that the group that put the RDF rendering together had to meet was called round tripability. I'm sure there's a formal name for it, but I couldn't find it. And the notion is that if you start with an internal FHIR structure definition of a resource, such as the diagnostic report, if you convert it into FHIR RDF and you convert it back into the internal representation, you will neither add nor lose information in that process. The same rules apply to XML and JSON, and so you can start with FHIR RDF, convert it into the internal model, and pull it out in XML, or you can start with JSON, convert it into the internal model, and pull it out in RDF. One of the things you're going to discover that I find a bit annoying, but there it is we've got a Boolean variable here, which it's FHIR Boolean, and it's the person active flag. It's got an inner B node where the value is Boolean, and you say, well, dadgummit, it's a Boolean variable. RDF knows about Boolean. Why don't we just put it in there directly? The reason behind that is that FHIR is infinitely extensible. It's extensible all the way down to the core data types. So it's theoretically possible for somebody to create an extension to the Boolean variable. This is just a hypothetical example I threw in where we wanted to put in a certainty, which is a decimal type. And the rule on, well, round tripability and what have you, is that anything that's, if you know about the extensions, you can see them and process them. But if you don't know about the extensions, you can just ignore them. So I can take the person active, and if all I know about is the Boolean, I can process this value. And the idea is that I'm none the wiser whether there's an extension in there or not. So that's why that inner B node shows up in there. Now, talking a little bit about round tripability, a couple of the things we had to do to make that work. The first one is we've got a node in here, or an element in here, that you don't find in the other representations, called tree root. And the reason for that is both XML and JSON have the notion of a document and the outermost node of a document. There's no equivalent in RDF. It's quite possible to have multiple subjects, some of them which are contained or in the XML or something are contained inside the diagnostic report, and others of which are on the outside. So the node role tree root tells us where to start reassembling a FHIR resource if we're going to turn it back into the abstract syntax. The other thing you're going to find are this FHIR index entries throughout here. For those of you familiar with RDF, it has the collections layout that was done by the list people, where you have the first entry in the collection and the rest of the collection, and it ends up being an interesting nested structure. A lot of communities aren't really interested in dealing with that these days, and that was the decision of the RDF community. So instead, what we have is we have just a set of inner nodes, and the index determines the relative order of these nodes when we assemble them back into XML or JSON. Some other things in here, however, are actually extensions that we're able to use in the RDF rendering. They're all optional, so they don't have to be there, and they don't actually add information to the RDF, so it's okay to put them in and when converting to the RDF, and remove them when they come out. And these are the important bits that make what we're doing today work. If you look over at the JSON representation of a coding, you have the FHIR code system, which is a URI, the code, which is a string, and display text. If we look at this in RDF, we can add an extra element, which is a type arc, or we represent as a type arc. So we're actually putting in the URI of this SNOMED CT concept. This URI is as determined by the SNOMED International Organization, so it's a standard. And if you dereference, or if you go through the prefix, what that's actually saying is that this is an instance of this particular concept code. Another place where we put something in is if you look at the JSON for the subject reference, you've got a reference which is a relative URI that's relative to the document or the document source. It's non-trivial to figuring out what the full URI is from this reference, and it doesn't follow exactly the same rules that RDF follows. So we've put in an optional field which is a FHIR link whose target is a URI, and for code that's rendering it in RDF, if they know how to assemble this URI completely, we strongly encourage that this link be put in here. Another element you'll find, it's kind of interesting because the spec itself says that the subject of a diagnostic report can be a patient or a device or a population, or I don't remember, there's another one in there. There's 4 possible subjects. And the FHIR spec says that in order to find out what the subject is, you need to dereference this URI, and it'll give you the type of what its target is. This doesn't work well if you don't have a lot of software between you and the target. If you're, for instance, using Protege, it's not easy to write a rule in Protege that figures out how to dereference this URI. So again, if you know what it is when you're putting this together, and if you're using FHIR examples, it turns out that you can actually parse the relative URI or the absolute URI and determine, this is most likely an instance of patient. So you can put in a type arc that tells you what it is. The final thing you're going to find is the ontology and import declaration. It'll be easier to talk about why that's in here a little bit later when we get into what we're doing. Let's see. Okay. As far as the concept URIs go, to get it in there, oh, actually I didn't fill out the WHO standard. I need to get that fixed in this slide. We're trying to get the various organizations that publish concept definitions to tell us what they want their URIs to look like. SNOMED International now has a standard that says if you want to publish SNOMED URIs, they look like this pattern here. And very nicely, if you dereference a SNOMED URI, you will actually get vectored to a SNOMED International server. I think it's the SNOMED browser that tells you something about that URI. The good news, or the good thing about that, is it's not forgeable because you can't forge SNOMED.info. The DNS system covers it. So if you use the base URIs of the organizations that publish it, you can know that it's correct. You can know that it's a valid code. The WHO has a standard that I didn't fill in on this slide, but it's on the WHO.int website for the ICDs, the ICD International classifications that work the same way. We're working with HL7, and I think are pretty much settled on what their URIs are going to look like. And we're going to have to, I think there's a de facto standard showing up for LOINC, but that's something that's underway. So, given this background, given that I've got RDF with these extra elements in here, what's interesting now is that we can start using this RDF directly into a DL reasoner. Our goal is to take an instance of one or more FHIR resources, essentially a collection of RDF triples that represent data in FHIR, to feed it into a reasoner, to define particular classes and categories that we're interested in the reasoner, and to determine whether a given resource instance, a given subject, is or is not an instance of whatever class we put in here. So in this example, I said I want to put in a class called cancer diagnostics, and what I'm interested in is any diagnostic report that has a type of malignant neoplasm in it. Okay, so if we generalize this, we're feeding in FHIR resource instances, a set of classification rules, and drawing conclusions. Okay, the first step we need to do is if we're going to feed FHIR resource instances into a reasoner, the reasoner has to know how the predicates, how the classes and predicates are used inside that instance. We actually have to say whether this predicate is an object property, an annotation property, a data property, and we have to say that various types are classes and what have you. So that's the instance descriptions. So if I start with an example resource data record here, this is the one that we were looking at earlier, or a bits cut out of it. What we've done is we've produced, we're calling it the FHIR Metadata Vocabulary. You will sometimes hear it referred to as the FHIR Ontology, but that tends to get a little confusing because the FHIR Metadata Vocabulary is about FHIR resource instances. It says nothing about patients, specimens, diagnoses. What it talks about is patient records and patient references, specimen records, diagnostic reports, etc. And as I said, it supplies the necessary information. It's derived automatically from the FHIR structure definitions. It tells our reasoner that a diagnostic report is an L class, which means that when we feed in a particular instance of a diagnostic report, we have an instance of a FHIR resource. It says that a report code is an object property, as is a coded diagnosis. It says that FHIR value is a data type property. What's fun about this, or what's interesting about the FHIR metadata vocabulary, is that every class and predicate that can appear in a valid FHIR RDF record is defined in here. And in fact, what we've sort of constructed, or what fell out of this without us really thinking about it, is the equivalent of a Dublin core for clinical data. We have a set of RDF tags now that we can use in Well, in FHIR RDF, but we can also use it to mark up HTML or XML, saying this is a patient reference. This is the diagnosis code as defined by FHIR. That will actually allow us to map things from other formats in and out of FHIR. It's OWL compatible, so you can load the FHIR Metadata Vocabulary into a Protege reasoner and look at what's in it. And the types, it's you know, it says diagnostic report has you know, 0 or 1 identifier. If you drill down into this in a different section in Protege, we actually use the cardinality axioms. But the important thing is this is the identifier record in the resource, or results in the resource. Now, this gets, I talked about the ontology header a while back. This is a good time to return to it. What's interesting is if you go out and fetch one of those URLs, either off of the website I've got or the FHIR server, and if you don't have this ontology header in here, when you load it into Protege, it thinks that every one of the dang predicates in there is an annotation property. Even if you have FHIR.ttl, the FHIR Metadata Vocabulary, loaded in advance, you still get exactly this. We've talked to the Protege people and a bit to the people that do DL reasoners, and there's an interesting and an arcane reason why it works this way. I'm not sure I understand it, but that's how it has to be. So the net effect is, in order to load a resource and have a DL reasoner, not just Protege, but any DL reason saying, you have to import FHIR.ttl inside the resource itself. This says, okay, for the predicates you find in here, you treat them as object property assertions, classes, etc. And the only way, since the RDF community never settled on how one might do RDF import, in order to do an import, the easiest thing is to say, well, I'm an OWL ontology. You know, how much I've got to do with OWL is an interesting question, but if you declare yourself to be an OWL ontology, you can then leverage the OWL import space. So that's what's going on here. And every FHIR resource that you pull off of a FHIR server will have this ontology header put down at the bottom so that you can use it in reasoners. So we've got the resource instances, which is the example there. We've got FHIR.ttl, which is the instance descriptions. The next thing we need to talk about is the concept references inside the instances. So this is where that type arc I had in the earlier example comes into play. This reference is snowmed.info, and it's the malignant tumor of the craniopharyngeal duct. Because it uses standard URIs, I can just load a standard OWL image of SNOMED CT into Protege, and these links work. The fact that this diagnosis is an instance of a diagnosis of the malignant tumor of the craniopharyngeal duct is what's needed. It's also going to force us to start to get a little more rigorous with our ontologies, because there's in SNOMED elsewhere, there's the body part, or I don't remember that it's not a finding site, but it's there's the thing called a tumor. It's not a diagnosis of a tumor, it's the actual thing. And that's one of the frequent errors you'll find in SNOMED coding, is that somebody will put in the code for the body site rather than the code for the disease rather than the code for the diagnosis. The type arc kind of makes us honest here. And in fact, if there weren't a diagnosis of the craniopharyngeal duct, we'd have to put in a post-coordinated phrase to make that happen. We'll talk about post-coordination a bit more. Anyway, once you get in here, you learn all sorts of things about these tumors, and you have the full wealth of all the information SNOMED's gathered about it. Down here. Okay, the other place that we reference ontologies is from the classification rules. The rules we're going to write ourselves. This is a sample rule. I I realize I'm throwing L functional syntax at you right away. David had asked, can't you just put this in Turtle? And the answer is we can, but it gets long and kind of involved. When you're writing L, you're a lot better off with the functional syntax when you're writing class declarations. What we're doing here that's of interest at the moment, we'll touch on some of the other in a little bit, is I'm declaring a class called a report with cancer diagnosis, and I'm saying, okay, it's equivalent to any subject that has a FHIR diagnostic report coded diagnosing predicate, and that is whose target is an instance of the SNOMED CT concept for malignant neoplasm. The other things you'll find in here is that the classification rules need to import their little mini ontologies. This is an ontology with basically one class. I need to import SNOMED because I'm referencing that. I need to import the FHIR Metadata Vocabulary. And one way to do it, and for these examples, I go ahead and import the diagnostic report. There are other ways you can do this without actually having to import it, but that's the one that makes it easy to show. The other thing I'll touch on briefly is if we look at the diagnostic report, we've got a nested B node. It turns out that the property chains in L are real handy, and I can say, okay, I shouldn't have really declared this in the FHIR namespace, but I'm going to declare a new predicate called coded diagnosis coding. And I'm going to say it's the equivalent of a property chain where if you start with a coded diagnosis, you go inside it, you find a coding, it's the same thing as this property chain. I think we touch a little more on that later. So the key is, however, is I'm referencing another concept inside SNOMED CT. It's at a different point in the tree, but again, I'm tying into the SNOMED CT space. So in the example I've had, we've got the SNOMED CT cancer subset that we're pulling in. I'll talk a little more later why it's a subset, but this is one of the L ontologies. We can pull others in. I've got the classification rules I showed you. I've got the reasoner. Now, to show how the reasoner works, I use Protege. You can use a reasoner without Protege. You can just feed it to it direct, using the L API. But if we pull it into Protege, I start by loading the classification rules I showed earlier, and all of these are available on a GitHub site that David published. One of the things that's worthwhile doing is making sure that everything that was in that cancer report, in fact, got imported into Protege. We've got these catalogs out here. If you don't have the catalogs filled out right, Protege tries to have a dialogue with you about where you might find stuff. And for various reasons, it can end up being a tad painful. So, but making sure that I've got everything in, I've got the actual report, I've got the SNOMED ontology, I've got the FHIR Metadata Vocabulary, and the FHIR Metadata Vocabulary references W5, which is why you get that down there. Okay, select the FACT++ reasoner. You have to use FACT++ at this point. Neither Snow Rocket or Elk at the moment will deal with everything that we've got in here. Fire up the reasoner, and what you get done with, well, it's sort of underwhelming. Nonetheless, this particular diagnostic report that we were looking at has actually come down as being an instance of a report with a cancer diagnosis. Pretty useful. Now, pretty quickly, though, we look at it and say, well, earlier we talked about the fact that a subject could be a patient, a group, a device, or a location. And we're probably just interested in patients. So as another example, let's put in an additional classifier that recognizes diagnostic reports that are on patients. So I've defined a class called patient report, and I've said, okay, it's equivalent to all links that are type FHIR patient. So as long as we've got that type arc, as long as we've got the URI for the patient and the fact that it is a FHIR patient, this becomes a class that recognizes reports that are about patients. Another thing that we note is that we've got a report status. And it can be registered, partial, preliminary, and chances are if we're running a filter, we're not really interested in preliminary information. So again, this is just hypothetical to show how things work. If we follow the diagnostic report status link, we find that we have a code for final, but as we look it over, we say, well, actually, you know, I don't want to ignore things that are amended. I'm not positive whether they're final or not. So what's interesting is I'm going to make a decision locally saying that I believe that the amended reports also fit in our definition of a final or finalized report. So if I create a classifier for that, it's interesting because I don't have URIs in the FHIR for the moment, or at the moment. The current spec doesn't have URIs for the status for type code. So I have to go ahead and code in the text for amended, appended, corrected, and final. Again, on the bottom of the slides, there's links to all of these. So as I'm sure you already noted, this is a tad on the brittle side. I went out to a code system hierarchy at a given point in time and flattened it out as a set of strings. I didn't record any clue that I was using this code system. And to boot, I'm using data property constraints, which add complexity to the reasoning process. What we've proposed and is underway is that we really need to publish all of the internal FHIR code systems, the statuses and various things they use to make FHIR work as OWL. This is an example of our proposed representation for the diagnostic report status. If we've the URL of where you can actually find the OWL representations down there. If we can pull that in, then we can treat it as a full-fledged OWL ontology. And now we're back to, we have URIs for all of the codes. And I can rewrite the diagnostic report. If I have this type arc status, a final, I can rewrite the query now so that it's an object class of final report, and I'm saying all final and all, in my view, all final and all amended diagnostic reports are of the final status. More importantly, if I want, I can publish this little bit here as its own ontology, or feed it back to whoever's maintaining the diagnostic report. But the key is we stay in the URIs, and if somebody decides to add a new type to final, like like really final, if somebody decides that one of the amended types isn't really final, that happens, and we don't have to rewrite our code or even change the content. So I've gone through 3 of these. What I can do now is create one more class declaration where I put them all together. I can say, okay, final patient report with cancer diagnosis. I can import the 3 class definitions I defined already, and then I can declare a final patient report with cancer diagnosis being the intersection of all things that are about patients, all things that are final, and all things that have a cancer diagnosis. Pull it into the reasoner. This is what it looks like in Protege, and run the classifier, and indeed we fit. Now, for this talk, I haven't talked about negative use cases, but we do work through those as well, making sure that if it isn't final or if it isn't about cancer, it doesn't show up here, and that's obviously the sort of testing you'd want to do to use this. Well, one thing about this is so far this is interesting, but only so interesting, because I can go out to SNOMED and essentially say, give me all of the descendants of malignant neoplasm, and I can put them in their own table. And then if I want to answer this query, is this really a cancer diagnosis? I can say, well, is the diagnosis code any of the 50,000 entries in this table? And in fact, when we do this, this is most often the way we do it, is we just do the subsumption hierarchy. But we don't have to just do subsumption. This is an example. You can put post-coordinated expressions inside FHIR. You don't have to code it just as a single SNOMED code. You can put it in, they're talking about SNOMED CT compositional grammar. And what I've recorded here under the code is something that says it's a malignant neoplasm, it's a malignant tumor, right? A malignant tumor with whose finding site is the left lobe of the thyroid gland. A compound expression. Now, we don't do this today. If we encounter something like this, the RDF servers do not transform them. But a correct transformation would be a declaration like this. The fact that, okay, this is actually an instance of a malignant tumor, and simultaneously an instance of something that has a finding site of thyroid gland. The other thing you're going to note here is this intermediate property, the 609096. This is role groups in SNOMED. If you're going to do compositional expressions, you have to know about role groups. And where it's shown with the curly braces here, without the curly braces, it says something else. We could come up with another grammar that didn't, but just be aware that this sort of transformation from SNOMED compositional grammar to OWL fragments is not something you want to try at home. You want to count on software that does it. Now, what's interesting about this one is I can now create a classifier that says, tell me whether this is a disease of the thyroid gland. So we're now talking two hierarchies. The fact that a malignant tumor is a type of disease, and the fact that, back up a slide here, right, and the fact that the left lobe of the thyroid gland is a part of the thyroid gland. And so this actually does require a reasoner. It's not real obvious how one could assemble all of the information one needs to answer this query. And but if we put in this particular diagnostic report and run it against, see, I don't have we'll run it against the example I showed, we indeed do classify it as a report of thyroid disease. Before folks get too excited, does this solve the term info problem? The answer is no. I looked at it first and said, oh boy, you know, RDF means we don't have to do term info stuff. But if you pick this particular example, the X-ray, there's an A in there by the way, the X-ray imaging study, they've combined underneath a study series, they've got a predicate that's a body site, and they've got another predicate that's a laterality. There's nothing in this model that says the laterality is subservient to body site. These are both concept codes, and while it wouldn't make sense, an equally valid interpretation might be that it was a left, let's see, a left thing that was of type wrist, which is kind of an odd thing to say. The key really is that there's tacit knowledge in these information models, and somehow the additional information that's the tacit knowledge has to be made explicit before we can classify this. We really have to go from a separate body site and laterality into something where we realize that the laterality is actually a restriction on the body site. In a way, another way to look at it is that we might need to take this and produce a compositional code for the body site here. So this problem is still here, and it turns out the problem goes all the way up because we had to assume that diagnostic reports corresponded to SNOMED CT findings and diagnoses. That was a tacit assumption we made. There's a lot of work going on in FHIR right now to add semantics to the models themselves. If you start looking around, you're going to find SNOMED CT links that talk about what diagnostic reports are about and finding sites are about, etc. But we're also going to need some other sort of tool to make this work. As I said, the tacit model is in the data. The modelers know that the laterality is about the wrist. We don't. There's a couple of different paths going on that we need to watch. The first is that Graham Grieve and Linda Bird are working with a combination of the FHIR mapping language and the SNOMED CT template language to transform resource instances into SNOMED CT statements. The other place to look is the Shape Expressions group is doing some work, some interesting work with shape expressions-based mapping, which is sort of an XSLT for RDF. And we may be able to do some micro transforms there. No guarantees, but that's where we're going. Okay, some of the issues and some of the things we've come across here. If you download the FHIR Metadata Vocabulary from the FHIR STU3 site, or any FHIR site right now, your OWL reasoners, if you try to use it, are going to choke because it uses some data types, 3 or 4 of them, that aren't recognized in the OWL spec. The copy we have on the GitHub site that we link to at the end, we've done some edits on that to fix that problem. We need to reconcile that with the FHIR group. We don't yet have any value set references in the FMV. It's an ongoing task. Another interesting thing is I showed the property chain early on where I went from the diagnosis, coded diagnosis through to the code. There's some ideas that either within the FMV itself or with an extension that we have standardized paths that you can use in RDF and reasoners to get down to what you're interested in without having to go to all the difficulty of writing property chains, which are non-trivial. FHIR and RDF, what we'd like to see happen is URIs for all of the concept codes. We didn't have a URI for the status. We want to get that in. We want to see whether we can't get OWL rendering for all of the code systems. And one thing is the extensions that we have in RDF, those aren't really RDF specific. It's the fact that you can actually produce a concept code URI would be equally useful in XML or JSON. Same for knowing the type of the reference link. So there's a discussion, I said RDF profile, I think we were going to call it a linked data profile, is to put in a small profile that describes what it means for any FHIR resource to be conformant to the linked data space. When it comes to the reasoner, I had subsets. At the moment, the FHIR metadata vocabulary has some constructs in it that both Elk and Snow Rocket choke on. So we have to use FACT++. And if you're familiar with reasoners, FACT++ can classify SNOMED CT in about 20 minutes, at least on my machine. And that isn't useful. So what we're doing in the short term, and there's instructions on the website, is we're generating neighborhood subsets of SNOMED. We're putting in the, like for instance, malignant neoplasm, we put in the concept code so that we get all of the types of malignant neoplasm, the ancestors and descendants and everything it touches on. And that gives us a small enough set of SNOMED that the classifier works in sub-second to a couple second time. We've had a little talk with Michael Lawley, and once we get things settled out, we're fairly confident that we can produce a Snow Rocket reasoner that will deal with all this stuff. That said, if we're going into a production environment, if we're going to be watching resources go through a clinical system, many transactions a second, we're going to have a different model. We're going to have a classifier that has everything in it that's pre-classified, and a service that you can just feed small sets of RDF triples to, and have it run a series of decisions and give you the results. I also mentioned this, there's still some content negotiation issues. Some of the FHIR URLs, if you put them in, you can say _format equals turtle or TTL, and it should give you back the turtle the turtle reference, but when it does a redirection, it loses what you want. We also just have a basic mismatch in that Protege asks for application XML plus RDF. Now, Protege can parse any form of RDF you feed at it or you throw at it. It doesn't need the XML form, but we don't really have a MIME type that says, I want something an L reasoner can understand. So we're just going to have to talk with the FHIR community and Protege so that when it asks for the turtle the RDF representation, quite correctly, of a FHIR resource, we get it in RDF. So we've shown some samples of how FHIR RDF can be seamlessly integrated with DL. There wasn't any code in the middle there. We had to do a couple of edits, but we were able to pull it directly into the reasoner and go. DL reasoners give us a lot of power, a lot of things we wanted to do, but it still doesn't solve the term info problem. If you have disparate bits of data that modify one another, you still have to do transformations on the information model. While there's rough edges involving the classifier, we've done enough legwork and looking at other implementations that we're confident that with some effort and the old adage of software, but not a huge amount of software, we can actually come up with a production level classifier. Credits, some grants. Also want to give creds to Eric Prudhomme, David Booth, and Dr. Go-Chin Chang, who supports my work here, as well as a whole bunch of people that have worked with the W3C Healthcare Life Sciences team and the FHIR community as well. The presentation materials, if you go to blending FHIR and RDF and drill down, it works. I'll also note that it's got a SNOMED CT directory that has instructions on how to build your own subsets if you want to try different things. Questions, comments?
So thank you very much, Harold. This is awesome progress, and it's great to see a working example that demonstrates how FHIR RDF can be used. So the first question, is there any chance you could turn this into a tutorial?
Yes, we're doing kind of mini tutorials as parts of other presentations, both at the FHIR Developer Days in November, and we'll be talking about this again in tutorial mode in the Semantic Web for Healthcare Life Sciences Conference. We've also, hopefully we'll have a paper on this. We've submitted it to the Semantic Web for Healthcare Life Sciences.
Okay, next question. So is FHIR RDF fully compatible with the XML and JSON forms of FHIR?
With one minor exception, yes. And the one minor exception is actually an issue with JSON. It turns out the FHIR specification says if you want full round trip ability with JSON, you have to augment the native JSON parser and recognize trailing digits in numbers. FHIR requires you be able to know the difference between 1.0 and 1.00. JSON doesn't recognize that difference. With that one exception, and again, that's a JSON problem, to the best of our knowledge, it's completely convertible.
Thank you, Harold. And yeah, just to comment on that, that is definitely the goal of this FHIR RDF work. So if there are any incompatibilities that do show up, then they are bugs that need to be fixed. But okay, next question. What was the value that RDF provided specifically in this work? Could this have been accomplished some other way? What do you see as the net benefit of RDF?
Well, it sort of could be accomplished another way, but the lingua franca of the Semantic Web and Protege is RDF. If we're going to use a reasoner, one way or another, you have to convert whatever information you have into an OWL-compatible format. What we're getting out of FHIR is a full-fledged, a valid declaration of an OWL individual that fits directly into reasoners, and we don't have to put any software or any transformations in the middle. I guess the short answer is yeah, but you'd probably have to do in your own code what's supplied in the RDF on the FHIR website anyway, and getting that RDF out is not trivial. You might as well just use what the servers do.
Next question, how much of this work was already done and available, and how much of it did you specifically have to do for this particular use case of looking for cancer diagnoses?
Almost all of it was already available. As I said, there's some rough edges. I had to work a little bit to figure out how to make Protege fetch FHIR resources and how to fill out the catalog.xml. Everything else in there came directly from FHIR. I obviously wrote my own categories, but not a lot else.
Next question. How many knowledge sources are a part of FHIR other than SNOMED CT?
Well, there's certainly the standard, the link, RX norm. I've seen some DICOM scattered throughout there. I've noted some ICD in some of my perusings through there, HL7 V2 and V3. But as the resource, as the domain and applications of FHIR expand, I'm expecting to see some of the OBO, the gene ontology and phenome ontologies and other things fit in as well.
Next question. Can you elaborate on semi-realistic data? I think this may have been in reference to a comment that you made.
Oh, well, I was mostly grumbling about the fact that the sample data I'm using used F201 both as the identifier of the patient and the identifier of the document. The set of samples you can get off of the FHIR site that we were looking at are exhaustive, and some of them are contrived, some of them are derived from real sources. But we've been working in other environments with some of these the Cynthia data generators and the Smart on FHIR sample sets that are large and very realistic. One of our goals right now, the FHIR server itself and the one that Graham Greaves supports publishes FHIR RDF out of the box as a stopgap measure. We have a tool written in Python, because that's the language I use, that will convert any FHIR JSON into RDF, so you can point the tool at any web server and get RDF out the other end. We're hoping to get particularly the HAPI and the FHIR tools to be serving this relatively soon.
Next question. What are your explanatory comments on importing FHIR in Protege?
If you go to this Yosemite Talk web page and scroll down, there's a description of everything that's there and hopefully a useful set of instructions on how to actually use it. If there's problems or issues, feel free to file an issue report or submit a pull request or whatever's needed to make sure this is accurate. But I don't know that's what it's referring to or not. Okay.
All right. Next question. As you said, there is an error in SNOMED, code of the disease instead of code of diagnosis. Do you think FHIR will be better knowledge source?
It's not an error. It's actually SNOMED and they're working through making a fairly rigorous model of this observations working group. The error isn't in SNOMED. The error is in treating SNOMED as a lexicon, as pulling something that has the words that, you know, it says a tumor of the pituitary or pituitary tumor, and assuming that it's referring to the diagnosis of a finding of tumor of the pituitary, where it may be actually referring to a thing, knowledge about what tumors of obituary do. So it isn't an error in SNOMED. It's until we start applying reasoners, and until we, in fact, to the semantics I was talking about that Graham and Linda and others are adding, some of these errors are going to go undetected. And it really doesn't matter as long as all you're doing is looking at the text. But when you start doing this, all of a sudden the logical definition and where it appears in the hierarchy becomes terribly important.
So in other words, if someone makes a coding error and chooses the wrong SNOMED code, then the reasoner could potentially detect that error.
Exactly.
Complain.
In fact, we would hope it was caught earlier when they're putting together the value sets. Now that we can actually apply logic, it's time to make sure that we're actually saying what we think we're saying.
Okay, good. Last question: is FHIR a generic healthcare vocabulary? If so, do we need to augment a domain-specific ontology?
I think that's at the moment where the reason I don't like to use the word FHIR ontology for FHIR.ttl. It's a really good vocabulary of what can be said in the healthcare record. At the moment, it's not very good at all about the practice of healthcare, and it's not its job. Its job is to document standardized records about healthcare. SNOMED and other ontologies are where you need to actually start linking to the knowledge about healthcare itself. So much like the Dublin core is a set of common tags that you can, and it's metadata for documents. It's how you record who wrote it, who reviewed it when it was written, etc. The FHIR.ttl is a catalog of things that you can say in healthcare records. And that's incredibly valuable.
Well, thank you very much, Harold, for a very enlightening presentation. And thank you very much to our audience for participating. If anyone wants to receive notice of future Yosemite Project events or webinars, just visit yosemiteproject.org and join our email announcements list. Thank you again to all, and goodbye for now.